If you're training reasoning models with GRPO, increasing your rollout size is just, it's not going to save you on hard tasks.
No, it really won't.
You're basically just paying massive amounts of compute to watch your model flail around in the dark.
Yeah.
Today, we are looking at a brand new paper titled TAREC, Distill to Explore, Reinforce to Refine, by researchers at LinkedIn, Harvard, and Georgia Tech.
It's a fantastic read.
Yeah, and here's the bottom line for the ML engineers tuning in. GRPO is great, right? But it stalls on hard prompts because the model literally can't randomly stumble onto the right reasoning path. TAREC solves this by using a teacher model, or remarkably the model's own augmented context, to generate a verified solution.
Right, a verified path.
Exactly. Then it filters for solutions closest to the model's current weights, applies a quick forward KL update to drag those solutions into the reachable search space, and then lets standard GRPO take over. This massively accelerates learning on hard math and agentic tasks.
It's a huge breakthrough.
It really is. So welcome, all of you, to AI Paper Slop. Our mission for today's deep dive into the source material is unpacking exactly how to break through this exploration bottleneck in on-policy RL.
And it's a mission that, it gets right to the heart of current AI training bottleneck.
Oh, absolutely.
Because the reliance on purely on-policy methods like GRPO has driven a lot of the recent leaps in reasoning.
Yeah.
By generating multiple answers to the same prompt and, rewarding the ones that do better relative to the group, training stays closely tied to test time behavior.
Right, which is usually what you want.
Exactly. But as this paper brilliantly highlights, that on-policy property is kind of a double-edged sword.
Yeah.
When we start pushing these models into highly complex, long-horizon tasks, those foundational assumptions just begin to fracture. I mean, you can't reward a behavior the model never natively exhibits.
Okay, let's unpack this. We just stated that TAREC fixes GRPO on hard prompts. But to really appreciate that fix, we have to deeply understand the baseline problem for the engineers listening. Like, why does GRPO hit this wall in the first place?
It's a great question.
Think about standard GRPO like a teacher grading tests based only on what a student randomly guesses. Imagine a student taking an advanced calculus exam, but their baseline knowledge is so low that they just keep guessing basic algebra.
Right, they don't even have the tools.
Exactly. They try 16 different algebraic equations. The teacher looks at them, says, well, these are all completely wrong, and gives them all zeros. There's no relative better or worse to learn from.
Yeah, they're all equally useless for calculus.
Right. And if the student never, just by sheer chance, writes down a correct calculus equation, they get zero positive reinforcement. So they just keep sampling structurally similar wrong answers in a tight loop.
Yep.
They're exploring, sure, but they're exploring a barren desert.
That barren desert is exactly where most training runs for complex reasoning models actually die.
Wow.
And if you're an ML engineer listening to this, your first instinct to fix a stalling model is probably going to be, let's just scale up the exploration.
Just throw more compute at it.
Exactly. You might think, I'll just increase the rollout group size.
Yeah.
Instead of sampling 16 trajectories, I'll do 64 or 128.
Just brute force it.
Right. But as this paper shows, larger rollout groups will not save you if the reward modes are fundamentally unreachable under the student's current distribution.
Yeah.
You're essentially just more densely sampling that same barren desert.
Because the verifier isn't the problem here, is it?
No, not at all. The verifier is perfectly capable of recognizing a correct calculus equation if it actually sees one.
Right.
The scarce resource is exploration coverage of the actual solution space.
Ah, I see.
So the problem isn't assigning better credit to sampled behavior, it's how to make useful behavior sampleable in the first place.
Which brings us to the T-ARC framework. Because if random exploration is just sampling at a desert, doesn't standard distillation just drop us into an oasis we don't even know how to navigate?
That's a really good way to put it.
Like, if the student is completely lost, how do we give them a hint without just handing them the answer key and ruining the whole RL process?
Yeah.
If we just force them to blindly memorize a teacher's output, aren't we just doing supervised fine-tuning? We'd lose all the generalization benefits of RL, right?
You would, and that tension is exactly what the TARC framework is designed to navigate.
Yeah.
It does it through a very specific staged procedure.
Okay.
So it deliberately avoids blindly applying distillation everywhere, The first stage is routing prompts based on difficulty.
Ah, okay, so it's selective.
Very selective. TARC estimates the unaided student pass rate for a given prompt, and it only activates the proposal mechanism on hard prompts.
He's finding hard prompts is what exactly?
Usually where the pass rate is exceptionally low, say below 12 or 15%. If the prompt is easy and the model is stumbling onto rewards natively, TARC just leaves it alone. Let GRPO do its job.
Okay, so we're preserving the RL dynamic wherever possible.
Exactly.
But when the model is genuinely stuck, we bring in a proposal source, like some massive teacher model, to generate verified candidate solutions.
Yep. But here is where it gets clever.
Right, because the genius part of the paper is that TARC doesn't just take any correct answer the teacher gives. It filters them for a metric called reachability.
Yes. Reachability is the key.
Because just because a 600 billion parameter teacher model can solve a math problem, it doesn't mean its specific cognitive leap is easily learnable by a small 8 billion parameter student.
Exactly. Finding the right path for that specific student is crucial. So TREC ranks the teacher's verified solutions to find the top R most student proximal proposals.
And they use a really specific metric for this, right?
Yeah, they use something called trimmed length normalized negative log likelihood, or NLL.
Which is great because most traditional distillation methods require you to have access to the teacher's internal states.
Right, the logits, the hidden layers.
The full probability distribution.
Exactly. But TREC doesn't need any of that. It only requires the text outputs from the teacher.
I want to break down the mechanics of that trimmed NLL metric for a second, because it's an incredibly clever way to measure true cognitive reachability rather than just string matching.
Go for it.
So when we measure how close a teacher's text solution is to the student's current weights, we look at the token losses.
Yeah.
But TRA trims the lowest 10% of those token losses.
Yeah.
And why do we do that? Well, because if you just look at raw losses, a trajectory might look artificially close just because the student model easily predicted basic formatting tokens.
Like the new line character.
Yeah, or the word step 1, or therefore.
Right.
So we trim the lowest 10% of token losses. So the model doesn't look artificially close just because it got formatting right. And conversely, we trim the highest 2%.
Which is just as important.
Right, we trim the highest 2%. So isolated weird outliers don't make it look artificially far. One bizarre vocabulary word from the teacher shouldn't skew the whole metric.
What's fascinating here is the operational freedom this text-only approach gives you. Because you're only relying on verified output trajectories and your own students' token losses to calculate this trimmed NLL, it is absolutely perfect for black box APIs.
Wow, so you don't need the weights of the teacher at all?
Not at all. You can use an external API as your teacher, feed its text outputs right into your pipeline, verify which ones are correct, and TREC figures out which of those are reachable for your local open weight student model.
That's incredibly efficient.
It really turns the proposal source into a sample selection engine. It suggests where the student should search next, but the verifier and GRPO still determine what ultimately gets reinforced.
Okay, but identifying the right path is only half the battle.
Sure.
If we use traditional on-policy distillation here to force those verified solutions into the model, don't we just run into the exact same wall?
Yes, we do.
We've routed the hard prompts. We've filtered down to our top reachable verified trajectories. We have our targets. Now, how do we actually update the model's weights before we throw it back into the GRPO arena?
Well, this is where we have to contrast TREC's approach with standard on-policy distillation, or OPD.
Okay.
Many recent alignment methods rely heavily on OPD, and OPD shapes the credit assignment on trajectories that the student has already sampled.
Right.
It redistributes probability mass among the options the model naturally generated. But in this hard prompt regime, the student isn't sampling the reward modes at all.
The correct trajectory is literally just not in the batch.
Exactly. So OPD fails completely here because there's no on-policy signal to redistribute. You can't shape the reward of a correct path the student never took.
Okay, let me introduce an analogy here to make sure this lands. Think of standard OPD, like trying to reshape a clay pot you've already spun on a wheel.
Oh, I like this.
You can push it, pull it, mold it, but you can only work with the clay that is currently on the wheel.
Yeah.
If the shape you need requires clay in a completely different spot, you are out of luck.
Yep.
TARC, instead, uses a short forward KL proposal learning phase. And forward KL is like forcefully throwing a brand new lump of clay onto the wheel exactly where the pot should be.
The clay pot analogy captures the mechanism perfectly. Forward KL minimizes the divergence by actively penalizing missing proposal support.
Right.
Because we've already verified that the proposal is correct, and we've verified through our trimmed NL metric that it's proximal enough to the student's current capabilities, Forward KL aggressively forces the student's probability mass toward that verified mode.
Highly targeted.
Very. It's a targeted update applied only to these carefully selected trajectories, dragging them into the student's sampleable support space. Once that new lump of clay is on the wheel, you hand it back to GRPO to smooth it out.
Okay, here's where it gets really interesting. When you hear proposal source or teacher model, the immediate assumption is that we need a bigger, better model to guide the smaller one.
Right, like using DeepSeek v4 to train a smaller model.
Exactly. But the paper proves that the proposal source doesn't have to be a separate external model at all.
No, it doesn't.
It can be the student model itself, using inference time context. The researchers call it the self-context variant.
And honestly, the self-context variant is perhaps the most elegant part of the entire methodology.
It blew my mind.
They augment the student model's prompt with a failure lesson memory.
Yeah, explain how that works.
Well, before the proposal generation phase even begins, they collect a bunch of the model's failed, verify or rejected attempts on these hard prompts.
Okay.
Then they ask the model to summarize its own mistakes into a set of generalized transferable rules. During the actual proposal generation, they simply prepend these rules to the prompt.
The paper gives some great specific examples of these rules, and they're surprisingly nuanced.
They really are.
Like it'll say, don't blindly apply Fermat or Euler theorems. Verify that the greatest common divisor of A and M equals 1 first.
That's a great one.
Or check small cases. Do not stop at the first plausible value. By simply adding this inference time context, the exact same base model suddenly discovers verified solutions that it was entirely blind to just moments before. We take those newly discovered solutions, run them through the reachability filter, and apply the forward KL update.
It's brilliant.
But wait, let me play devil's advocate here. I want to push back on this.
Sure.
If the model knows how to solve the problem, as long as we prompt it with its own past mistakes, why do we need this whole forward KL training phase? Why not just always deploy the model with that long augmented prompt? Isn't it just easier to use good prompt engineering?
Well, it is a tempting shortcut, I'll give you that. But relying on inference time scaffolding comes with massive structural costs.
Like compute costs.
Yeah, prompting a model with its past mistakes consumes a significant portion of the context window. It dramatically increases the inference compute cost for every single query.
Right.
Plus, it relies on brittle prompt engineering that might not generalize well to unseen domains. The ultimate goal of reinforcement learning is to expand the base model's unprompted capabilities.
But isn't it cheaper to just pay the inference cost than to run an entire forward KL training phase? We're talking about modifying weights versus just passing more tokens.
Over the lifecycle of a deployed model serving millions of queries, the inference cost of bloated context windows vastly outweighs a targeted training update.
Okay, fair point.
But beyond the economics, it's a profound philosophical shift.
How so?
The self-context mechanism proves the model already had the capacity to solve the problem. The knowledge was latent in the weights. What it lacked was the navigation to find that solution without a crutch. The forward KL phase is what actually bakes that navigational capability directly into its base weights for deployment. We use the scaffolded context to eliminate the path, but we use forward KL to pave that road permanently.
Wow. Okay, so what does this all mean? When we look at the actual benchmarks, does this theoretical elegance translate to empirical proof?
It absolutely does.
Let's start with the math benchmarks. The researchers tested TREC across math and agentic tasks, looking at AMI 2024 and 2025 using Qwen3 deployment models at the 1.7 billion, 8 billion, and 14 billion parameter scales.
The math benchmarks provide a very clear validation of the routing and consolidation theory. If you look at the Qwen3 8B model on the highly difficult AMI 2025 dataset,
Which is notoriously hard.
very hard, standard direct GRPO achieves a 36.9% accuracy. But when you apply the 2Rec framework using a large DeepSeek v4 teacher model as the proposal source, that accuracy jumps to 40.3%.
That's a huge leap, but what's really impressive to me is the self-context variant. Using just its own failure lesson memory without any external teacher, that same 8B model jumped to a highly respectable 38.5%.
Right.
That proves the architecture works even when you're completely constrained to a single model family and have zero access to external APIs.
The gains on math are undeniable. But the results on the agentic tasks reveal an even deeper dynamic about the exploration bottleneck.
Let's get into that.
For these tasks, the researchers used the Quinn 2.57b instruct model on the ALF World and Science World benchmarks.
Okay.
Mathematical reasoning tasks, while complex, are relatively self-contained. You generate a chain of thought and you output a final number. Agentic tasks, however, require multi-step procedural reasoning.
Right. Over a long timeline.
Exactly. The model has to interact with a simulated environment over a long horizon, receiving feedback at each step.
This is exactly where sparse rewards become a nightmare. If we look at a task in ALF world, it's not just answering a question. Let's take a complex task like heat in place.
Oh, that's a perfect example.
The model has to navigate a simulated house. It needs to search cabinets to find a potato, pick it up, navigate to the kitchen, open the microwave, put the potato in, turn it on, take it out, and carry it to a specific counter.
It's a lot of steps.
That might be a 50-step sequence. And if the model makes one wrong move, if it drops the potato on step 49, the environment fails, and it gets zero reward.
The penalty for failure is absolute. Standard GRPO requires the model to randomly stumble upon that perfect 50-step sequence just to get its first positive reinforcement.
Which is practically impossible.
The mathematical probability of that happening through purely random exploration is vanishingly small. And this is where the paper's findings are so critical. TREC doesn't just raise the final asymptotic success rate, it drastically accelerates early training.
Let's look at the numbers on that because they're wild. On the Science World benchmark, the standard GRPO baseline gets a success rate of 12.5%.
Yep.
But TREC with external DeepSeek V4 proposals more than doubles that, reaching 26.7%.
It's incredible.
But you mentioned the early acceleration, and the ALF World per task breakdown completely validates the theory of routing based on difficulty.
Oh, absolutely.
ALF World has different task types. The easiest tasks, like simple clean-and-place scenarios, they're already near the performance ceiling with standard GRPO. They sit around 92% success.
Right, because they're short.
Yeah. TREC pushes them to 100%, but the headroom there is minimal. GRPO is handling them fine.
But when you look at the hardest tasks, the tasks with the lowest baseline performance, the difference is just staggering.
Yes. That heat-and-place task we just talked about, the baseline success rate is 59.5%. With TREC, it jumps an astounding plus 19.1 points.
Wow.
And another complex multi-step task, Examine and Light, jumps plus 12.6 points. The gains are overwhelmingly concentrated on the exact multi-step environments where the unaided student was just repeatedly failing.
If we connect this to the bigger picture, this early acceleration on hard tasks represents a massive paradigm shift for the economics of training AI models.
Compute savings.
Huge. Agentic rollouts require constantly querying simulated environments. Every step takes time and compute. They are incredibly expensive and slow compared to standard text generation.
Right.
If your model has to rely on pure random exploration to stumble upon the solution for a complex task, it might require tens of thousands of wasteful environment interactions before it sees a single reward.
It's literally paying thousands of dollars in compute just to watch your model open and close a virtual microwave without the potato.
That is exactly what's happening. But by using a proposal source to find a verified solution first, filtering it for reachability, and injecting that multi-step solution mode into the student's support before the RL refinement begins, TR saves a massive amount of that compute.
That makes total sense.
The student enters the GRPO phase with the hard task trajectories already sampleable. It shifts the economics of training agentic models from a brute force search into a highly targeted optimization process.
It's just so elegant because we are using distillation, but we aren't using it for brawn, mindless imitation. We're using it as a surgical tool for exploration, support, expansion.
A surgical tool, yes.
We find the specific blind spots where GRPO is failing. We map a reachable path through those blind spots using a teacher or self-context. We consolidate that specific path with forward KL, and then we let GRPO do what it does best, refine and optimize based on verifiable rewards.
We aren't asking the student to become the teacher. We are simply using the teacher to ensure the student has access to the full landscape of possible solutions before they begin their own optimization journey.
Right.
It completely reframes distillation as a navigation aid rather than a destination.
That brings up a really provocative thought, actually. One that the authors touch on in the conclusion of the paper.
Oh, the continual learning part.
Yeah. We've been talking about this entire framework in the context of a static training run. You have a fixed data set, a closed loop, a cluster of GPUs. But if this stage decomposition propose, filter, consolidate, refine. If it works this well for hard prompts, could this be the blueprint for true continual skill acquisition in deployed models?
It is a staggering implication for the future of deployed AI. I mean, imagine an autonomous agent deployed in the wild.
Okay.
It encounters a brand new software environment or a novel domain it has never seen before. Naturally, its baseline on-policy exploration fails. It doesn't know what to do.
But instead of just failing permanently and requiring the developers to start a massive data collection effort, the system dynamically spins up a massive inference time context window.
Yeah.
It pulls in external documentation, reads the error logs, uses step-by-step execution feedback, and through sheer brute force scaffolding, manages to solve the problem just once. That single success becomes the proposal.
And then the magic happens during idle compute time.
Oh, I see.
The system takes that single, verified, reachable trajectory and applies a quick, targeted forward KL update locally.
Wow.
It permanently consolidates that brand new skill into its base wakes on the fly without ever needing a massive cluster-scale retraining run.
So the model learns a new skill exactly when and where the exploration bottleneck occurs.
Exactly. And then seamlessly integrates it for all future unprompted interactions.
It's a glimpse into a very different, very exciting future for autonomous agents. A future where models don't just optimize what they were trained on in the lab, but actively expand the boundaries of what they can explore in the real world.
It's definitely the next frontier.
You will definitely want to keep an eye on how this architecture evolves over the next few months, especially as models move further into agentic workflows. We'll be watching it closely. Thank you for tuning in to the deep dive into the source material on AI Paper Slop. We'll see you next time.